Good morning, sir. Today we're going to present about free space optic performance. My group members are Kishantan Krishnan, Sheshan Armugam, I'm myself Gayatri Saravanan, Shalini Kesaraja, and Nick Hilmi. What is free space optical communication (FSO)? It is optical communication technology that uses light propagating in free space to wirelessly transmit data for telecommunication or computer networking. The important benefit of FSO is it has high data rate transmission comparable to optical fiber communication system. FSO is capable of transmitting up to 2.5 gigabits of data, voice and video communication over the air without need of fiber optic cables with operation between 780 and 1600 nanometer of wavelength bandwidth. FSO transform require light which can be obtained using light emitting diodes, LEDs or lasers. The major advantage of FSO are it no need authorization is demanded for transmission of laser beams due to air as transport medium. It has shorter maintenance time since installation is fast and easier. It has capability to operate at advanced power condition and offers larger and lower bit error rates BER. Okay, in this project we studied on FSO standard single channel transmission with multiple channel transmission by using WDM and the performance of FSO WDM on effect of varying beam divergence in terms of BER and Q factor. Okay, WDM, which is stands for wavelength division multiplexing. WDM is a technique that multiplexes signals of different wavelength to be transmitted over an optical fiber. It's a revolution in optical communication network because it allows the capacity of the system to be increased simply by increasing the number of channels and tightening the channel spacing without use of multiple FSO link. We can say that WDM technique can be used in FSO system to maximize bandwidth usage. Okay, we can see the example WDM picture. Next, I pass to Shalini.
Shalini, we can't hear you.
Okay, hi sir. So I'm going to talk about the research methodology. The entire research was carried out using the simulation program, which is Opti system. The main purpose of simulation is to find the best system configuration for maximum performance and then implement it on the application system. And also, OptiSystem software is a cutting-edge optical communication system simulation tool capable of designing, testing, and optimizing practically any type of optical connection in the physical layer of a wide range of optical networks, from analog video broadcasting system to intercontinental backbones. So, if come to this flow chart, in the beginning of the research, we have to do the title of the project, which we decided was free space optic performance, and therefore we have to use the suitable software, which is Opti system, to design circuit regarding optical fiber. And also we have to plan and decide what type of circuit to use and how to design it. After the design, we have to run and simulate the circuit to get the result which we expected. After that, we have to record the data from the result we obtain. So let's go to the research setup. The purpose of this research is to demonstrate a free space optical communication link using a normal single channel transmission and a multiple channel transmitting system using 4 WDM, which is wave division multiplexing. So the free space optic communications employ the optical transmitter to create point-to-point line of sight links that communicate over the air. So the diagram over here is about the transmitter converts electrical impulses into optical signals and sends them into the air, and also the receiver converts the optical signal to an electrical signal. In order, the result of the transmitter is routed into an optical multiplexer for the 4 channels into one FSO channel for a single network. All channels were multiplexed and placed into the FSO channel through the optical multiplexer. So the FSO channel is made up of an optical attenuator and a noise added in decibel per kilometer. The attenuator reduces the signal of the input optical signal by the amount provided. So these are the block diagram. So the first block diagram is the single channel transmission system, and the second one is 4 channel transmission system, which is used by WDM receiver. So next I pass to Sheshan.
Okay, okay, you guys can see the screen now.
Yes, can.
Okay, a very good day, sir. My name is Shishan Armugam. Okay, for the demonstration for the first part, which will be the FSO single channel, this will be the layout as what Shalini explained by using the block diagram as the reference, we construct it. So it's content of FSO transmitter, FSO channel, and FSO receiver at the end. Okay, for an overview, we can say that the data generated by the PRBS generator at a bit rate of 50 Gbps is stored and light modulated using a laser source, which here will be the CW laser with a frequency of 1550 nanometer and a power of 50 dBm. And then and then we the modified light is amplified through optical amplifiers before being sent across a distance of 5 kilometers where we set here, and with optical gain set at 2 dB. And at the end, the amplified signal is transmitted straight to the receiver, which started from the photo detector to the BER analyzer. So what we did for vary our result, we changed the beam divergence to produce different shape of the eye diagram, as well as the Q factor and the BR value. Okay, so this will be our figure 7 in our report, which we can say that the system with a beam divergence of 0.5 m radius has a better Q factor of 10.0953 and a lower BR value of 2.88823 exponent negative 24. Then for figure 8, we change the m radian to 0.6 to vary our result. Okay, to vary our result, then what we can say from here is the Q factor which we get will be 7.11344 and the minimum BR value of 5.64 028 exponent negative 13. What we can say that this weakens the system since the Q factor falls and the BR value rises compared to the figure 7. So the last for the FSO single channel will be, we change it to 0.7. Okay, for figure 9 with a 0.7 m radius, this system has a Q factor of 5.29012 and a minimum BR value of 6.0891 exponent negative 8. This will be the weakest among the two since it has the lowest Q factor and the greatest BR value. So that's all for the demonstration for part 1. I will pass it to Kishon to explain the 4 channel WDM.
Can you see the screen?
Yeah, can see.
Okay. Now, say previously station. I sir, sorry, my name is Kishantan, and let's explain about uh, simulation integrating with WDM. So, as what session said earlier, we studied how a FSO works in a simple single channel. So, as the next level, what we did was we integrate the FSO technology and with the WDM technology. So we know WDM is like it's a multiplexing technique which improves the efficiency of the system in terms of bandwidth and capacity. Okay, so for demonstration, what we did was um, we chose 4 by 1 multiplexer. So it'll be receiving 4 transmitting source, and which will be transmitted through the channel, and at the receiver end it will receive. So as for the transmitter, similarly, we use a 5 gigabit data rate, which the laser source of 15 dBm. So for all the 4 transmitters, this power was 15 dBm. The only thing varied was the frequency, starting from 193.1 terahertz up to 193.4 terahertz. Okay, all these incoming signals will be modulated using the Mach-Zehnder modulator, and then will be fed into the multiplexer, and the multiplexer will collect all the multiple incoming signals and reroute through a single channel. Now here we use optical gain just to boost the signal. Okay, upon boosting the signal will enter into the FSO channel. Now what are the parameters in this FSO channel? First is the range. The distance we chose 5 kilometer, and the attenuation. All the parameters we just randomly selected just to analyze the system. So the attenuation was 10 dB per kilometer, and the transmitter aperture diameter was 5 cm, and the receiver aperture diameter is 50 cm. So we need to know that the transmitter aperture diameter must be lower than the receiver aperture diameter, so that at the receiver it can capture all the light sources. If the diameter is bigger, it can capture all the light sources even better. And then beam divergence. Okay, as session said earlier, our focus or analysis is done based on how beam divergence affects the system, right? So we'll be varying the beam divergence value and analyze the system. Okay, then upon entering into the FS channel, the signal will again enter an optical gain to boost the signal to get a better output, and then it meets the WDM demultiplexer, where all the signal will be demultiplexed and sent into the respective receiver. Okay, so at the receiver part, we'll be using a photodetector to capture the electrical signal. I mean, sorry, to capture the optical signal and then convert it back to electrical signal, and then a low pass Bessel filter which eliminates all the unwanted signal, and then the 3R regenerator. We include this to get the BR analyzer output value. Okay, so now as for demonstration, what I'll do is I'll change the beam divergence value to 0.5, and you will see the output. At receiver 1, we can see that the Q factor is 8.2, and the I diagram is like this, and the minimum BR value is 4.6 to the power of negative 17. Okay, the Q factor is 8.2, and for the second receiver is 7.9, and the third receiver is 8.2, and the last receiver is 7.79. So what I'll do now is I'll increase the beam divergence value to say 0.9 maybe. Okay, we'll see what difference it makes. Okay, just now the first receiver was 8.2. Now we can see the Q factor has been reduced to 7.1, and the I diagram also a bit distorted. Similarly, for the second receiver, the QR factor has been greatly reduced to 6.5, and for third receiver, similarly, it's been reduced from 8 to 7, and then the last receiver you can see 6.3. So what we can see is that if we increase the BER value, the quality of the signal is getting degraded and distorted. So BR value plays an important role in FSO technology. So yeah, with that being said, I'll pass it to Nick Elmi to conclude our assignment presentation.
Okay, as a conclusion, a single free space optic FSO were constructed and analyzed, designed to improve its efficiency. A wave division multiplexing has been integrated to FSO system using 4 channels with different frequency values. Based on the simulation result, we can see that by varying beam divergence parameter, we can influence the BER and the Q factor values. As we increase the beam divergence values, we can see it degrade the overall system's performance by increasing the VAR value and decreases the Q factor. Research show FSO system has high potential to become a breakout technology in coming days, but a major concern is in this system is that they are too reactive to the surrounding weather condition, which tends to impact the overall system performance. To overcome that, a properly planned and calculated design should be done ahead before the deployment. So I think that is all from our group. Thank you.
Thank you, sir. That's all for our group presentation. Hope you like it. Thank you so much.